Okay, so today we're going to continue our conversation on limits. We're going to talk about the concept of what continuity is in terms of functions and what the concept of one-side limit is. Now, a one-side limit is simply a limit where we only care about going from the left or the right-hand sides, left or right-hand direction. As you know from before, in order for a limit to exist on a graph, it needs to approach the same number from the left and the right-hand sides. Well, if I only care about the left-hand side, it doesn't need to agree with the right-hand side. I only care about the left-hand side limits. For these cases, you'll see, for example, like, of our limits, as x approaches, we'll say 2 of f of x. This is just a normal function. We want from both left and right-hand sides to agree in order for the function to exist. The left-hand side will have a little negative in the superscript position. This means from the left side. If it's a plus sign in the superscript position, this means we're talking about from the right-hand side. This distinction is very important for evaluating our functions on a graph, but if they're just simply functions given to us for algebra, like 1 over x plus 2, for example, it doesn't matter. We still plug in the number they give us, and that's our answer. Very straightforward. So I just went over that. Again, one-side limits from left to right only, plus signs for the right, negatives for the left. So, for example, if I want to evaluate the limit as x approaches 8 from the right-hand side, that's what plus sign means, of 1 over x plus 8, I just plug in 8. That's 1/16. Because remember, for the most part, the left and right-hand sides agree at that value. The only times they disagree are when you're dealing with piecewise functions, when they're approaching different numbers, there's like a gap between them, or you're valuing functions that have like absolute values. Not absolute values, sorry, vertical asymptotes. But for the most part, they're always going to agree. So if here the limit as x approaches 9 from the right, of x minus 5 over x squared minus 25, well, we plug in 9. We get 4 up top, 81 minus 25 on the bottom, which is 55. So 4 over 55, and that's as far as it goes. Always remember with your fractions to reduce it as far as possible. If you would like to write as a decimal form, that's perfectly fine. 4 over 55 is a decimal. It would be 0.0727. I always do 3 numbers after the decimal. The 0 I don't count as an actual number. I wanted 3 actual digits. It's whatever your call is. Pretty much whatever your teacher wants you to do. Alright, so for this example, we're asking limit as x approaches 3 from the left. So again, we plug in 3 for x. And something interesting happens in this particular case. We get 3 divided by 0, which does not exist. But I want to go a little bit further than that. Okay, yes, it doesn't exist, but I want to know where does it exist? Because 3 over 0 is an infinity value. We're approaching either positive or a negative infinity. I want to know, well, which one is it? So in order to figure out which one it is, whether it's a positive or negative infinity, either you can graph it and see what happens, or you can plug in a number that's really close to this value from the correct direction. So if I'm coming from the left direction, I want to see, well, let's plug in like 2.9 for example, and see what happens. So we have 3 over the square root of 2.9 squared. 3 over the square root, so when I square our 2.9, we get 8.41. And this is really nice. This makes your life a little bit easier, because just because it's over 0 doesn't mean it's always infinity, because in this case, 8.41 minus 9 is a negative 0.59. Oop, that was my calculator, sorry. You can't take the square of a negative number and get a real result. So that's another reason why it does not exist. Because technically, 3 will exist from the right-hand side, but it cannot exist from the left-hand side. Because everything before 3 from the left, there is no function. It doesn't exist as an actual value. So that's why the answer still does not exist. This is important because, again, there will be sometimes they'll ask you whether about it's a positive infinity or a negative infinity for different answers. And if you want to know, you must always, again, plug in a little bit to the left. In this case, because coming from the left is something that doesn't exist, that's another reason why it stays as does not exist. Limit as x approaches 0 from the left of square root of x over x. Well, if we plug in 0, very quickly we get 0 over 0. And the reason why is because the absolute value function is really a piecewise function. The absolute value of x is really negative x if we're less than 0, positive x if we're greater than 0. And it's just simply 0 if x equals 0. That's the middle point. Well, if I'm coming from the left-hand side, that's everywhere that's to the left of 0, that's this value right here. So this really is equivalent to negative x over positive x, which is just negative 1. And that's how you handle piecewise functions for these kind of limits. You want to do is you see, okay, if I'm coming from the left-hand side, which one is to the left of this? So which one is less than 0? If it was from the right-hand side, this was a plus, I'd go which one's bigger than 0 and pick out that value. That's how the piecewise functions work. So for example, if I want to find the limit of f of x as x approaches 3 from the left, where this is my f of x function, I must find what is to the left of 3. So this first function is when x is less than 3. Well, that's to the left. So I'm going to work with this one. So I'll plug in 3 into the x plus 2 over 2, and get 5/2. Very straightforward. Important thing to remember with our piecewise functions, if it's talking about just x approaches 3, for example, I would have to plug in both top and bottom to see if they agree. Because remember, the limit only exists if it's approaching from left and right at the same time. So if left and right agree, then it exists. If they disagree, then it does not. If I only care about the left or only care about the right, you just plug into whichever one is appropriate. The left for when it's less than, to the right when it's greater than. So this example, as I said, because I'm talking about x approaches 1, not left or right, left and right must agree. So I must plug into the left direction. From the one from the left, we'll do 1 cubed plus 1, which is 2. And then from the right direction, we'll plug into the one that's to the right, greater than 1, which is 1 plus 1, which is 2. Since they agree, the value of the limit is 2. The value that they both agree on. If these two were different numbers, then the limit would not exist. So it all depends on do they agree with each other or do they disagree with each other. And that's how you evaluate the piecewise function limits. Left is the less than, right is the greater than, and if it's just looking for in general at 1 or at 7 or negative 5 or whatever, it must give you the same number. Now, the concept of continuity. A function is continuous if there are no holes or no vertical asymptotes on the graph. Essentially, if you were to have your graph in front of you, if you could trace the entire function without ever taking your pencil off the paper, the function is a continuous function. Again, have to trace the entire one. If you have to take your pencil off because you have got a hole and you got to go to a different spots, or you got to take it off because you have a vertical asymptote, or whatever reason, it is not a continuous function anymore. And if it's discontinuous, there are two different types of discontinuities: a removable discontinuity and a non-removable discontinuity. A removable discontinuity is one where you can easily fix the function by redefining the function at that discontinuity. For example, a hole. It is very easy to fix the hole because all you got to do is just simply plug in an actual number there. Fill it in with a circle. You can easily fix that. Non-removable is one where it's impossible to fix a function and keep it really a function. These exist when you have a vertical asymptote or there's a gap in the graph. Piecewise function, we're approaching 2 and then 5. There's a gap between them. You can't fill that in. Because to fill in those particular cases, you need to draw a vertical line in there. And a vertical line is not a function, therefore you can't keep it a function. That's why it's non-removable. Also impossible to fix vertical asymptotes because, well, they go to infinity. There's no way to trace that if it's going on to infinity. So what we want to do is we want to find the x values, if any exist, where this is not continuous. And then discuss the discontinuities, if they are there, whether they're removable or non-removable. Again, if this was an actual graph, it's really easy. You just look at the graph and see, okay, is this fully continuous? And if it's not, at any point you take your pencil off the paper, that's the area where it's not continuous. And if it's a hole, it's removable. If it's a vertical asymptote or gap, then it's non-removable. Now, functions like this, where just simply x squared minus 9 are nice polynomial functions, are always continuous. Because again, remember, discontinuities only occur at holes, gaps in the functions, or vertical asymptotes. All three of those require it to be a rational function, or at the very least a square root function, or something else going on. If it's just simply a nice polynomial function, there's no way it's never discontinuous. You can plug in whatever x value you want, you will always get an actual number. Either it could be really, really big, or maybe really small, but you always get a number. That's why it's continuous. Again, notice, we have a rational function, it's a fraction. These are where you'll generally have your discontinuous functions. It doesn't have to be discontinuous, but this is where it generally is. Now, if you remember how to graph these from pre-calculus, the key is always to factor top and bottom to see if things cancel out, to see if you have vertical asymptotes from the bottom, holes, that kind of stuff. So if I factor x squared minus x, we take an x out they have in common, leaving x minus 1. The denominator equals 0 when x equals 0 and when x equals 1. These, since the denominator nothing cancels, are both vertical asymptotes. So what we have for this particular problem is a discontinuous function because it has vertical asymptotes. Discontinuous. At x equals 0 and x equals 1. Since they're both vertical asymptotes, they are non-removable. Again, vertical asymptotes will have you have that. Vertical asymptotes will be non-removable functions. Holes will be removable. Why don't you give this one a try on your own? Again, factor it because that's the key with rational functions. If things cancel out, that's a hole. If things don't cancel out, whatever is in the denominator is a vertical asymptotes. Again, if things cancel or you have a denominator left over, it's a discontinuous function. The key is whether it's removable or non-removable. So for this particular problem, because when we factor the x squared minus 25, we cancel the x plus 5s. Again, canceling things tells us we have a hole. The hole will occur at -5 because that's the x value that happens for these two to cancel. Because there's a hole, this function is discontinuous. Because it's a hole, though, this is a removable discontinuity at the value x -5 because it's, again, a hole in the graph. So that's how you're going to discuss the different continuities for actual functions. Again, given the actual graph itself, this is incredibly easy. So when you're given just the function without a graphic calculator, it requires you to use a little effort. Okay, so that's it about one-side limits and discontinuities. Again, always remember, plus sign means from the right side, minus sign means from the left-hand side. Alright, so next time we're going to start talking about infinity for these different limits.